We're on air. Yeah. Excellent. So, thank you all for putting up with the change of timing. So it turned out we're actually clashing with the Pure Math seminar, and after some discussions we decided it's better not to clash, because today's speaker is obviously of interest also to our colleagues in the Pure Math group right next door. So Svante is based at Uppsala. He's contributed significantly to the theory of random graphs. I mean, he has several books. I've read 2 only. And I'm very happy to have him speak today about the configuration model. So please.
Yes. So, yes, I'll talk about components in the configuration model, as Sophia said. Now I know that people have varied backgrounds, so my plan is to go slowly, and plan is to start with some old things that most of you will, I hope, know and maybe find a bit boring, and then I'll continue with the newer and newer things, and then at the end I'll come to really new things, and by then maybe some of you will find that too technical and boring, but I hope that you'll find some interval in between interest. And I should also say, beginning, because I forget later, that what I'm talking about in later parts here will be about a joint work, partly about some old joint work with Malwina Luczak, and partly about recent joint work with Malwina Luczak and Remco, which we are still working on trying now to complete here while we're here at Newton Institute. So the general problem is, of course, not restricted to this model of random graph. We have a graph and or a random graph in this case, and we want to study its components. We know that typically, now we know since the discoveries by Elders and Reni from around 1960, that in many random graph models, typical situation is that either the graph is, say, what's called subcritical, when it's so sparse, so we have only a lot of small components. But then we have the other case when we've got more edges. We tend to have one big component like this, and then outside that only some small ones. So this has now been seen and shown in many different contexts. So this is what we regard as the natural situation. And it's also now intuitively rather clear why it ought to be like this. I mean, if we have enough edges, then we certainly expect that we will have some big components. And also, it's quite natural that we cannot have more than one really big component, because it would be very unlikely to have 2 components with a large number of vertices, but not any single edge in between them. At least, I mean, this, what I says now, is for type of random graph models I'm talking about here, where we have no say, special structure, no kind of geometry and so on. If we have like geometric random graphs, or if we look at percolation models on a lattice and so, things are different, but I'm not going to talk about that. At least partly different. So we expect this thing, we have one big component and small components outside. And one natural way to study this is to explore the components successively. We start by picking a vertex, and then we make a breadth first search. Here we look at all its neighbors, and then we look at their neighbors, and this maybe don't have any more neighbors, and maybe this. Okay, and now maybe I've run out of neighbors, and then I know that this is a component. But if I happen to start here in the giant component, then I will go on for a very long time and find new neighbors. until I found the whole component. This is one of the main techniques to study component size. I think it's not the only one. I mean, I think if I remember correctly, the original work of Erdős and Reni, they found a giant component by first looking at the small components and counting how many there are, and they saw that in the supercritical range there just isn't enough of vertices in the small component, so they have to be in the big one. But this more direct method is often most direct, best approach. So the idea here is that we do exploration, and we can look at it two ways. We can look at it, say, from the outside like this. Suppose we have the graph and we already know where the components are, and then it's obvious what happens is what I just did. We pick a vertex at random, and if it happens to be in a small component, well, then we find the small component and it's quickly over, and then we go on and pick another vertex and find the next components on. But if we happen to pick a vertex in the big component, then we'll find this big component. So that tells us in particular that if we have a component here which is of size proportional to number of vertices, then we have some rather large probability of finding this one as the first component. If not the first one, probably it will be the second or third, or in any case we'll find this component fairly quickly. Whereas a small component, of course, can take a long time until we find. But then we can also look at it, say, from the inside. If we just do this exploration without knowing anything, we just go on in the darkness here and know only what we've seen. So then we start by picking a vertex. Let's make a new graph. You don't know what's in there. Here is a vertex. We find its neighbors. So in the beginning will be some tree like thing, and then either it will suddenly die out or it will continue. And in models, many random graph models, what happens here initially can be very well approximated by a branching process. So if we start with a random vertex, and it has some random number of neighbors, and each of them will give us a new random number of neighbors. And as I said, in this type of random graph models here with no geometric structure, so this will be asymptotically independent, centrally independent. So in the beginning this will be just like a branching process. And that is very useful both as intuition and as a proof technique. So I'll come back to this later, but let me remind you right now that the important thing with branching processes is that they are either finite or infinite, and if the expected increase each time is at least, well, expect down on new vertices where is at least more than one each time, then we have a with positive probability get an infinite branching process. But if it's less than 1 or equal to 1, then with probability 1 it will be finite and probably quite small. So, and now of course I said this was an approximation of the neighborhood exploration process. Of course this can't go on forever. If we have an infinite branching process, that can not be a good approximation of this finite exploration forever, because certainly we have a finite graph and will not find an infinite component. So of course what happens is if we really find a big component, then after some time this branching process approximation will be a bad approximation, because we've used up so many vertices and tend to find cycles and other things. But the intuition is that if the branching process is infinite, then we are in a big component. But exactly how big is a little bit more difficult to say. And if the branching process approximation is a small finite, then that will correspond to a small component. And as I said, the crucial thing is whether the expected number of neighbors will be, of new neighbors, is more than one or not. So now, this was some general background, and today I said I'll talk about random graphs with a given vertex degrees. So the general ideas I mentioned already, Eggers and Reni and their work, they, as you know, looked at completely symmetric random graphs with no structure at all. We just have a number of vertices and then throw out edges at random. In their case, a given large number of edges, or you can do the GNP model with independent, put in edges with some edge probability P, essentially the same thing. If you look at the vertex degrees in that model, they will be asymptotically Poisson distributed. And that's a good model for many applications, but for many applications you want to be more flexible, and in particular you want to be able to find out the vertex degree distribution. So nowadays it's very fashionable to have degree distributions with heavier tails, in particular power law distributions. That is certainly not something you will not get with the Eggers-Reni graph, but there are other models to get it, and this one is one way to get it. So the idea is that we just specify what the vertex degrees are. We are going to have n vertices, and we have degrees d1 up to dn, which are given somehow by us. We can choose them. And then we want to take a graph, let's say dn, dr, maybe we can denote it. This is uniform random graph on vertices. The vertices are labeled from 1 to n, and vertex degrees, the number of edges are just this given numbers d1 to dn in this order. So it's a sequence degree. So now there is one one technical thing here. So when I say uniform random graph, it means we just look at a set of all graphs on this vertex set with these vertex degrees, and we pick one uniformly at random. So the first problem is that we have to know that there exist any such graphs at all. And there is one obvious necessary condition. The sum of the vertex degrees has to be even. That is, of course, not a very interesting thing in this context, but it's a technical nuisance, so we have to assume that. And there are also other conditions here. I mean, we have some general conditions by Eggers and Golai on degree sequences of graphs, but they are not important because I'm looking at fairly sparse graphs, and I'm interested when n is very large. I'm actually interested in asymptotics as n goes to infinity. And in that case, in the case I'm interested, will be no problem. As long as the sum is even, there will always exist such graphs. But there is another thing. As I said, I'm really interested in asymptotics. So if I let n, I will let n go to infinity. But next question, what do I do with the vertex degrees? So what I really want here is not, you could say the simplest thing would be to say you have a sequence of degrees and let n go to infinity, but that's not really what I want. I really want one model for each n. So I really want degrees that depend on n, for each n. And then I let n go to infinity, And then now, at least today, I'm talking about the sparse case where I have some finite average degree here, and even more I want to have some specific distribution of this, limiting distribution of the vertex degrees. So I want say that if nk is the number of vertices with degree k. So if then I want this nk divided by, so this is the proportion of vertices with degree k. This should converge to pk for some probability distribution pk. Okay, some say probabilities pk, k going from 0 up. So this will be the asymptotic degree distribution. And I find it useful to have notation here, dn, capital D for random variable. This is defined as the degree of random vertex. So I pick one of the n vertices at random and look at its degree. So it's just picking one of these numbers, d1 up to dn, with equal probability. And then this thing here is precisely the probability that dn is equal to k. And therefore what I say here can also be written as saying that dn converges in distribution to d, where d has this distribution, probability d equal to k is pk. Of course, this is at least kind of notation I'm used to phrase things in terms of these random variables dn and d instead of numbers here. But of course, you can easily translate with different notations. So this is the setting here. And as I said, this model is attractive because it is quite flexible, but still it has a lot of independence. So, of course, you can achieve any degree distribution here. Since you are choosing the degrees yourself, you can get precisely what you want. If you want a power law tail, then you just choose your dn's. Well, of course, what you do is really you choose your asymptotic degree distribution d, and then you choose your d1 for each n. You choose your d1 to dn, or really, as I said, they depend on n in a suitable way. And I may comment here that one way to do this, which some people like, is to say we start with a degree distribution d. So now this is a distribution on the integers, unbounded typically. And for each n, we pick n independent copies of this random variable and say that these are our degrees d1 up to dn. Well, not really, because we have that silly problem that with probability about a half, the sum will be odd, so then we have to modify it a little. But if we do that and get an even sum, then we do this construction and have a random graph and so on. So in that version, these vertex degrees are by definition random with some given distribution d. And that as well, that version has some advantages, I admit that. And if you want to model with some given asymptotic distribution, this may be a natural way to do it. But it has other disadvantages. And the main thing I think is that it's, I see that's a special case of this more general thing where you really choose arbitrary distribution with some just asymptotic properties. So I prefer to define model in this way because it's more flexible and you can choose your degrees in other ways too, if that's useful. And I mean, I have examples of that, but I'm not going to talk too much about this. And also I should say that sometimes it's a technical advantage to have these random and can simplify some estimates on. But just this thing that we have to make the sum even means that we have to, as I said, to adjust the degrees. So the degrees will still not be completely independent, just almost independent. But as you know, in probability theory, independence is very useful. So it's very good if you can make something independent. But to have something almost independent doesn't help that much technically. So to know that something is almost independent is not almost the same as knowing that they're independent. For said, technically it's not good, but in any case, it's one way to do it, but not the only one. Now, I said that one reason you want to do this is maybe you want to look at graphs with heavy tails. But another reason, which I think was maybe the first use of this type of random graphs, is that you want the opposite thing. You want to have all degrees the same, a regular graph. So that's also an example. We have random regular graph. All di are equal to d for some given fixed. Well, of course, you could look at these which increase with n also, but I'm not going to do that, because that, as I said, is different, and they will not have this thing. So in that case, this asymptotic distribution is just a constant variable, fixed, concentrate one point. Now I've given you a definition here, which is a mathematical definition. Said was uniform all ways to it, but the problem is how you do it in practice. If you want to study this, it's far from obvious. Then, as you know, we have a well-known way to do it. The configuration model, which was formulated by Bela in the back row here, some 35 years ago, so I think. I'm not sure if did you do it initially for the regular case, or was it? I know that was one of the first applications, at least, of configuration model. But
because Erdős always wanted to study random regular graphs.
Yes,
but had no means of even going.
No.
That was the reason.
But then it was quickly realized that this was also useful to look at more general cases.
Immediately.
Yes, immediately. There was, yes, certainly.
I mean, it's no difference whatsoever.
No, but it is one important application of it. Well, so that's why I wrote this case here. Okay, so the configuration model, again, I guess that most of you know it, but the way we do it is that so since this is the standard way to study graphs with a given degree sequence, at least in cases like this, which are rather sparse. If you have very dense graphs, that's a different thing, but I'm not talking about them today. So therefore, the name configuration model has become more or less synonymous with saying a graph with given vertex degree. So configuration model is one said the useful way to get them. So the idea is that we have now given vertex degrees. So for each vertex, I take I call them half edges. So we just put down here 1, 2. If these are the vertices, we put down here is D1, D2, D3, D4, and so on. And then we pair these at random. Random. So this means by unique formula random pairing or matching. So maybe we pair this one with this one, and this one with this one, and this one with someone further below, and so on. Okay, and we go on until everyone is paired with something else. And now we can draw this as a, well, draw these edges. Then I think it will be something like, well, this was a different vertex. This will give us, in general, not really a simple graph, but a multi-graph, because as you see here, these two half edges happen to be matched to two half edges, the same vertex here. And we could also get a loop with two half edges from the same vertex or joined to each other. But, so of course that is a problem. We don't get what we want here really, but it's not so bad problem in sparse cases, because simple calculation shows that you will not get many of these, and for practical applications, if you sometimes you could just ignore these. But if we now want to have really the simple random graphs we want, what we can do is we condition on having no loops and no edges. So, say this, the configuration model really gives a random multigraph with given degrees. D1 to Dn. And now condition on being simple, which means no loops and no multiple edges. And then the point is, as calculation shows, that this of course gives us a simple graph with a given vertex degrees by definition here, but it is really uniformly distributed all over. So this gives a uniform random graph, the one we wanted. When I said that this in practice works well, that it's not so much a problem that with the loops and so on. And the mathematical statement here is that in cases we're interested in, this probability is big. It does not. So probability of this being simple, so that the conditioning works fine. This is say bigger than some constant. Or put it like this. I'm interested in asymptotics as we go to infinity. So I really want this to be something that doesn't go to zero. So let's take the limit in here. You really positive 0. This is positive if and only if the sum of the degrees squared is big O of the sum of the degrees, to be state thing, most general way. So what this says is practice. If we have a degree distribution here with finite second moment, then this thing will hold. Well, at least we can expect it to hold. And in that case, so if the degree distribution of finite second, asymptotic degree distribution of finite second moment, then modulus minor technicalities, this thing holds. So that means that with this conditioning here really is not bad. And mathematically it means that we can prove that something holds for the multigraph mod with probability tending to 1. It will still be true even after this conditioning, so it will work for simple graphs as well. There is still a problem, so that means if we prove something converges in probability, for example, it will still hold for a simple graph. If you prove that something converges in distribution to a normal distribution, for example, then we can't just do this conditioning, because that might in principle screw up things, and of course we don't expect that it will, but I have proved things where that takes a lot of extra work, but I'll not talk about such things today, but still are things that are not so simple. And then we also, of course, have the other situation if you really are interested in things where degree distribution does not have a finite second moment, so really heavy tails, then this thing is false. So the probability of the graph being simple goes to 0, and you have to, well, you have a problem. I mean, still it's possible to use this, and it is possible sometimes. I think Bela has proved some results where still doing this by showing that the error probabilities are even smaller than the probability that this graph is simple. So still one can use the conditioning argument. But if you want to study, for example, random regular graphs with high degrees going to infinity, so then maybe it's better to use other models, other methods, I say, than this model here. But for today's talk, I'm going to assume finite second moment here, and configuration model will work beautifully, and so on. Okay, so this was kind of introduction, and now I'm going to see what kind of results coming to. So first of all, for this model here, the main question is whether there is there a giant component or not, and that was by Molloy and Reed from 1995. So there exists a giant component if and only if, remember D was the asymptotic degree distribution. If this D times D minus 2 has positive expectation, or we can rewrite this as, of course, expectation of D squared is at least 2 times expectation of D. So first of all, why is this a natural thing? I'm not sure it was natural before they found it, but at least in retrospect it is very natural, because if we look at, well, as they say in the paper also, in good intuitive motivation of this, if we look at this branching process approximation talked about, so we think of the exploration process from the inside. Let's see what happens now in this type of random graph. We start with some vertex. We pick a vertex at random maybe. And we have some half edges coming out from it now in the configuration model. And then, well, let's follow one of the half edges. This will now be joined to some uniformly chosen half edge, all of them. So, well, it could be one, let's say, vertex, but that's a small probability. We ignore that. So will be some other vertex here. But this vertex will not be chosen uniformly. It will be chosen with a size-biased distribution. So, because we pick another half edge at random. So that means that this, let's say, vertex K here, vertex J, say, this is chosen with probability proportional to the degree, dj. dj over the sum of all the degrees, sum of dk's. Okay, and if we choose this one, then we get the number of new edges, new half edges is dj minus 1, because we are connecting to one of them. So this, so then dj minus 1 new half edges. So in other words, the number of new half edges is, if we go back to my notation with a d or d sub n perhaps for the n size n model here, we pick a, it's not dn, but let's take the size biased version dn star here, and then we subtract 1. where the probability of, so dn star is high spiced here. Version of dn, meaning that the probability of dn star is some k, is the probability of dn being k times k, and then we have to normalize, and the sum of this is just the expectation of dn. So we do modify d and in two ways. We make it size biased and we subtract 1. So then we can see that the expectation here, so that's the crucial thing in a branching process, is the expectation dn star minus 1. Well, if you use this thing plug in, you'll see that this expectation is just expectation of d times dn minus 1. And then we divide by the same normalizing factors here. So therefore, the crucial thing, as I said, is whether this is bigger than 1 or not. So this is bigger than 1 is equivalent to the expectation of dn times dn minus 1 is bigger than the expectation of dn. Or if you subtract, you see expectation of dn minus 2 greater than 0. And now if you do this asymptotic thing, put in the asymptotic distribution instead, you'd see that we have exactly the criteria that Molloy and Reed found. Now, their proof did not really use branching process precisely, but something similar. At least they did this exploration process, but you can do the exploration in two ways, which in one sense are equivalent. Namely, as I said, if you do it as a branching process, you start with the vertex, you look at its neighbors, and then you look in the next step at their neighbors, and so on. You get something which maybe is exponentially increasing if it's increasing here. But you can also do it more slowly. Say you explore one half edge at a time, and then you go on to the next half edge, and so on. And that will give you something which more looks like a random walk than a branching process. But of course, in one sense, it's equivalent, but that's often more, at least sometimes more convenient when doing it. And that's how they did it, and that's how I'm doing it too. But time has passed, so now I can do it in simpler ways than they did it. But nevertheless, this is the basic idea to this. So, if this now is the criterion for existence, as I said, it's not. Then it's not so. You can get this from, at least intuitively, from branching process theory, but this will not tell you how big the giant component is. Because, as I said, the branching process approximation breaks down for the big component. So that's general problem situations like this. You can study the small components without no problem, but you're really interested in the big one. You can also note that if there is a big component, well then of course you have to do things that show that there are not two big components, so there really is one. So, but that is not so surprising, maybe a bit technical, but so then we know that the size of the giant component is a probability that if we start the exploration at random vertex, we would really get a big thing. But so that is, if we have the random graph here. So I said if we start with a random vertex and go on now, try to follow what happens, then that will not be, the branching process approximation will break down, will not tell us how big the component is. But if we instead do it this way, that we look at it from the outside, we already know where the components are. One big here and lots of small ones if we now pick a vertex at random and see if it's supposed to be component the size rho times n, then obviously the probability is rho that we'll end up here, and when we start this exploration we'll find a big component, and the probability is 1 minus rho that if we'll start outside and just find a small component. So this means that we believe in the branching process approximation. This rho should be roughly the probability that this branching process will be infinite. So therefore we expect the size rho, or relative size, of the giant component to be equal to the, well, asymptotically now, the probability of survival for the branching process. Or, with offspring distribution, this d star minus 1. Okay, now I'm going to be now I'm going to be a bit more technical and see how one can do things rigorously. And one way, so what I'm going to do now is based on what I and Malwina did some years ago. So as I said, we can, one way to do this exploration is start at vertex and then look at a half edge at a time and see whether we get any find new half edges or new neighbors or vertices and their half edges or not. But and I mean that is also what the Molloy and Reed did. So they did it in discrete time, this exploration process. But I've often found it useful to do analysis of various random graph models using continuous time instead. And don't say it's always better, but in many cases it gives more flexibility and can enable you to introduce more independency things. So that's a generally useful technique, and that's what we did here. So we do the exploration in this way instead. So we take again here's the graph. Now we give each half edge clock, an exponential clock, which means that it rings, so it rings after a random time, after say exponential with mean 1 maybe time. So these times are random, and of course all clocks are independent. So it's an alarm clock where you wake up at a completely random time. And then we start by choosing let's say we start to select a half edge at random first, just to initialize things. And now we're going to pair that to some other half edge chosen at random. And the way to do that is that we just wait until the next clock rings. So start by picking half edge. Now wait until some clock rings, and pair these two half edges. So this half edge is in inverted rings, and then we join these two. And now when we do this, we regard the all vertices as sleeping from the beginning here, but now this one has been awake here by the alarm clock. So then all half edges at that vertex are now awake. This half edge and the one we start with, they are no use any longer. We can call them dead here, but the other ones are awake. So all half edges at this vertex are now awake. Okay, so then we go on, but now we pick instead one of the half edges which is awake. So pick half edge that is awake. Doesn't really matter which one. So we pick this one, say. Okay, and now we go back and do the same thing. We wait, and then suddenly someone here rings, and a half edge here. Okay, then we connect them, and then these are now awake. And next one, maybe is one here. Maybe this one didn't have any more half edges. This had vertex at degree 1, so that we don't get any new half edge here, but we still have the old one. So we pick this one, for example, and go on. Here's the next one that rings, and they connect. So this obviously gives us one way to do the exploration. And so you see the point here is that in a way we do the exploration and construct the random graph simultaneously. So of course that is a standard technique in situations like this. We don't reveal the random graph until we really need it. We rather construct it the time we're using it, which is very useful for the analysis. And in this case, it turns out now to be quite simple to see what happens this time scale, because let's look at the first. Let's first look at. Let's see, vertices. Let's say vk of t. This is the number of, say, sleeping. So we haven't found them yet. Sleeping vertices of degree k at time t. Well, we start out with nk of them by definition. So, but then we see that as long as, well, so they have by definition k half edges, so there are k clocks. If none of them has rung, then the vertex is still asleep. When one of them rings, then the vertex is awake. All the half edges are awake. So we have the probability of a time t of it still being asleep is e2 minus k times t. And well, this is really now, first of all, the expectation. But here all these half vertices now evolve independently of each other. All clocks are independent. So this is really holds with unprecision. Of course, you can make some precise amounts of deviations on standard things. But, we don't have to worry about it. Just say if you divide this by n to normalize things. So we can say this. This in our case will converge just to pk times e2 minus kt, converging, say, probability. Also uniformly over all t. And here we can of course we can prove this by standard estimate, Chebyshev inequality, if you want to prove uniform over T by some martingale inequality or so on. But you don't really have to do it, because you can notice that this is, you can think about the times when the first clock rings at the vertex as, or degree k, as independent random variables which are exponential with the mean k, intensity k, then this is just empirical distribution function of that set of random variables. So what I say here is just that you take the empirical distribution function will convert to a true distribution function, which is well-known standard thing in probability theory. I even found a name for it, Glivenko-Cantelli theorem. So we didn't have to work anything, could just quote standard theorem for this. And now if you sum this over k and look at the number of sleeping half edges, let's say S of t, you multiply this by k and sum, and you'll see that this will converge to the sum of all k, k times pk times e to minus kt. On the other hand, if we look at the number of all, say all living half edges, so these are the ones which are not paired. So this means not paired. We can argue in almost the same way. What happens is that as soon as any clock rings, that half edge is paired to someone else. So that means that we remove two half edges. Okay, so we remove them two at a time. So if we technically just divide the number by 2 and then see that it will be a simple depth process, same thing as here, but with twice the rate. So we'll see again from just look at the empirical distribution function that say this L, the number of this L of t will converge to e to, well, we don't have total numbers, so mu times e to minus 2t, where mu is the expected number. So that means if I subtract here the number of what I call active half edges, so this means that they are the ones which are used in they are found but not yet, we haven't explored them. So these are the ones we really work with in the exploration. If this now is A of t and we divide by n again, this is just the difference here. So it will converge to mu times e to minus 2t minus this sum k pk e to minus kt. So this is now some deterministic function which maybe looks like this typically. It's t, and here is this function f of t. So what is start at 0 because, well, if you check here, but also from the construction, obviously should start at 0, but this does if you check it. But more important is perhaps the derivative at 0. So if you compute the derivatives here, you get minus 2u plus the sum over k of pk times k squared, which, remember that pk is the distribution of my vertex degree distribution d, and this is the mean. So this is minus 2 times the expectation of d plus the expectation of d squared. So you will find again the Molloy Reed thing here. So in the subcritical case, this is negative or 0, and we will never get many of them. But in the supercritical case, it will start being positive, something like this, and then one can see that it will eventually become negative, because P1 term here will dominate for a large T, and it will be negative. So Okay, so this is the limit thing here. Now, there's one thing which is a problem here. This is a number of some half edges. This is obviously non-negative. And here I've just claimed it converges to this curve, which eventually is negative. And that's because I glide here a little. What happens is that it will follow this curve in the beginning as long as this stays positive. So, of course, some random fluctuation like this. But then when it comes here, it will certainly have to stay positive. So what happens is that it really will go on with some random fluctuations here. And that is because of this fact that we will, which I didn't mention here, when we have found a complete component, then we have to start again by picking a new half edge. And that is what keeps this process from becoming negative. So conversely, it's only when this would have gone down negative that we start picking new component. So one can see that in a situation like this, well, the components of precise excursions above 0. So maybe we have a few small components first, which we don't really see in the limit. But then here comes one big component. And then after that, we'll only find small components again. And this tells us that the size of the big component is given by what happens. Well, it's not the length. You have to count how many vertices you find, or how many vertices are being awakened in this interval. But that follows from these formulas here. So then one can write down an expression which it's not very illuminating, so I'm not going to do it. But that will tell us precisely what happens. And we also see that this will now be in the size scale we expected, and give us a proof of both existence and the size of the giant component here. Now I said I would at the end here talk about the recent things, and now I have less time than I should have planned for, so I'll be very brief. But what we do now is look at the critical case when okay, so the critical case is, of course, when the where we call it here, expectation of d squared is equal to expectation of times d. So in that case, this figure here will look something like this. But this means that we have to be more careful to see what happens with finite n. So let's say alpha n is expectation of dn times dn minus 2. So assume that this thing is positive, but it tends to 0 as n goes to infinity as some rate. And then we still can get same picture as before, but now we will have to scale time properly. So this will be much smaller, but we do it on a different scaling. And what's interesting now is that this will work precisely as before if the third moment of d is finite. But if we have an infinite third moment, but still, as I said, finite second moment, then we will have a similar behavior, but we need different scalings. We have a different size at the end. So I can state one theorem here that, don't call it alpha, sorry, we will call it epsilon n here. So if epsilon n is bigger than n to minus a third, and the third moment of this dn raised to 2/3, and this is really the right with, as Hatami and Molloy found. They found the size of critical window in this case. Then the size of the giant component here, or the largest component, maybe we should say. This is, yes, 1 over here. This is roughly, well, this mu we had before, times rho n, which still is the survival probability of the branching process. Now with offspring, but now we have to use this depending on n because things are more sensitive. So it's dn star minus n. So remember, dn star still has, this will still be supercritical, but as n goes to infinity, this will converge in distribution to d star, which is critical. So what happens here is that we have as n goes to infinity, sequence of distributions which are supercritical, but so the expectation is bigger 1, but we tend to 1. And then it's question what happens with the survival probability in such case, and that is something which was investigated by, among others, Athrey and Hop in around 1992, I think. So of course the survival probability will go to 0, but at what rate? And let's say typically this rho n is like 2 epsilon over expectation of this d n star minus 1 times d n star minus 2, if I remember correctly. If the third moment is finite, say this is finite, but smaller otherwise. But we say rho n is little of epsilon n if the third moment now goes to infinity. And this is a second moment of size bias 1, so this is really a third moment of the degree distribution. So I'll now, both because of lack of time and because I don't want to give unnecessary details here, but the point is that this, as I said, gives two different cases where if the asymptotic degree distribution has a finite third moment, we get this is just like constant, we get essentially the same as in the, say, Edwards-Renyi case, and we have a giant component with its size proportional to this epsilon n, with a proportionality constant which involves the third moment of the degree distribution. But if the third moment of the degree distribution is infinite, then we will still have an expression for the size of the large component, but it is smaller. It will be, some typical cases divided by the, I think, third root of the third moment, so I don't remember exactly. And there are, and in some cases it's more complicated than that, really, the complete formula. So one gets something, but there is a certain kind of phase transition now where when the third moment becomes infinite. Both the width of the transition window, a critical window, and the actual size of the giant component changes substantially when we, depending on whether the third moment is finite or not. But I would say that we prove this by using the same method as I showed before. You just have to be much more careful with choosing the right scaling here, which we do in a way which depends on this degree distribution d and moments of it in a not obvious way, and also more work to show that there is error terms are small, but the IDs are precisely the same. Okay, that's it. Now you missed 5 minutes of lunch already. Some of the technical things I left out.
Do you happen to know my paper with Oliver papers on these things?
I know some of them. That's
pretty precise results.
I know some of them, but I don't think I read all of your papers.
Down to the
yes.
Down to the critical value.
Yes, but I think I mentioned paper you had when you were able to do things also when you did not have second moments by some getting strong estimates.
I thought we proved pretty precise results.
Yes.
Down to critical value.
Yes. No, I remember that, even if I don't remember the results, but I remember your method, which was impressive. Yes.
In that case, thanks once again. Say your name and then continue in English.
Yes.